Hello everyone. Today we're going to do this problem. It's a heat capacity problem basically. So let me read it and we'll kind of go through it from there. So brass has a density of 8.40 grams per centimeter cubed and a specific heat of 0.385 joules per gram degree Celsius. A 15.2 centimeter cube piece of brass at an initial temperature of 163 degrees Celsius is dropped into an insulated container with 150.0 grams of water, initially at 22.4 degrees Celsius. What will the final temperature of the brass water mixture be? Okay, so basically we have this, this piece of brass. So we're just going to draw it out here in blue. Okay, so here's our brass. And this brass has a density of 8.40 grams over 1 centimeter cubed. Okay, and remember with density, we've got the units, grams per centimeter cubed, but we need to add the labels. And the labels in density mean we have grams of brass over centimeters cubed of brass. Okay, so those labels are super important. And brass has a specific heat of 0.385 joules per gram degrees Celsius. And that piece of brass is 15.2 centimeters cubed. Okay, so that's the volume of brass. Okay, and automatically, I see this is the volume of the brass. I can tell that I'm going to probably use this density to convert from centimeters cubed to grams. Okay, and so instead of giving the mass of this, they give the volume and the density to convert to grams. Okay, so this brass has an initial temperature of 163 degrees Celsius. And I'm going to tell myself that this is an initial temperature, okay? So I'm just going to label that. And it's dropped into an insulated container with water in it. So we're going to have this cup. Basically, insulated means that the temperature inside is going to stay inside. It's not going to exchange any temperature with the outside environment. Okay, so that's what the insulated means. So this container has water in it. Now this piece of brass is 163 degrees Celsius and the water is 150.0 grams. Okay, that's the mass. So we're going to call this the mass. And that temperature is initially 22.4 degrees Celsius. Okay, and so it's asking what the final temperature of the brass water mixture will be. Now this brass, 163 degrees, is hot. I should probably make it red, huh? So you can see that it's hot. Oh, my pen's not changing colors. Okay, so anyway, this is hot, 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 hot. Okay, and this water, 22.4 degrees Celsius, is about room temperature. Okay, so 72, 73 degrees. And so when I look at this, I'm going to do kind of like a little timeline here. Okay, or not timeline, but temperature. So my water is 22.4 degrees Celsius, and my brass up here is 163 degrees Celsius. Okay, now heat always travels from what's hot to what's cold. And so the heat is going to travel from the brass to the water, okay? And it's going to travel until thermal equilibrium is reached. Okay, so when thermal equilibrium is reached, that means the heat of the water, whoops, not the heat, the temperature of the water is going to equal the final temperature of the brass, okay? And so at that point, the brass has given as much heat to the water as it can, and T final is going to be the same. Okay, so the question asks us, what will the final temperature of the brass water mixture be? Okay, and so, you know, I've gone through and I've written all the variables up here, but one of the other important variables that's not given that you guys should probably have memorized is the specific heat of water. Okay, and so I've kind of written this all over. Let's see if we can squish it in here. So the specific heat of water is 4.18 joules per gram degree Celsius. Okay, so we can look and compare these two values. Because the specific heat of water is higher, that means it's going to kind of hold on to the heat a little bit longer. So it's going to give its heat to, so the brass is going to give heat to the water, okay, but the brass has a lower specific heat, so it's going to give up a lot more heat faster than the water will. And so I use that specific heat to kind of look on this temperature line right here to give me an idea of what my final answer should be. So if my brass is 163, it's going to lose the heat very quickly to the water. And so because of that, we should expect a value that's closer to the water. Okay, so it's going to take, so I shouldn't say, heat is kind of energy, right? So it's going to lose the energy and lose the temperature. And so my final answer, because the specific heat of brass is so low, it's going to be a lot closer to water because the specific heat of water is so high. Okay, so now, you know, I've kind of written all this stuff up, but I want to think about it with regard to Q, okay? So in this, we're adding hot brass to water, okay? And Q, or that heat, always flows from hot to cold. So I'm going to write this out here. So Q always flows from hot to cold until thermal equilibrium is reached. Thermal equilibrium says both have the same final temperature. Okay? So now I have to think about where that heat's traveling. And remember, we have Q of the system equals negative Q of the surrounding. Or I can say negative Q of the system equals positive Q of the surrounding. Right? Just one of these has to have a negative sign, one has to have a positive sign. And if you remember, these signs tell me what direction the heat is going. So here, this negative sign right here means that the system is giving off heat. Okay, so that negative sign means exothermic or gives off heat. Okay, and that positive sign right here means endothermic, or it absorbs the heat. So when you set up these problems, you have to think about what's giving off heat and what's absorbing heat. So we have our cup of water, we have our brass piece right here, we put it in, the brass is hot, so the brass will be giving the heat to the surroundings or to the water. So when I set this up, I have negative Q of the brass, because the brass is giving off the heat, equals positive Q of the water. Okay, so the brass is giving the heat to the water, and that's what that negative sign is, that's what the positive sign is. Okay, now if you remember, Q equals mCS delta T. Okay, so M is the mass, CS is the specific heat, And delta T is that change in temperature. So change of temperature is always, always, always temperature final minus temperature initial. So whenever you have a change of anything, if it's volume, if it's temperature, if it's heat, if it, whatever it is, energy, it's always final minus initial. Okay, so now if I go back to here, now I can substitute in these specific variables for my Q. Okay, and remember Q is heat, and heat's usually in joules. So when I look at this formula, I'm going to substitute these variables in for my Q. So I have negative MCS delta T, and this is for the brass, equals positive MCS delta T. Oops, that T got a little funky. And this is for the water. Okay, and remember that delta T is going to be final minus initial, but we're going to substitute that in when we actually put the numbers in. Okay, so write that down, negative at the first, and we're talking about the brass, negative MCS delta T equals a positive MCS delta T. Okay, so make sure you have those signs right, because it's going to make your math correct. So I'm going to go to the next slide. And remember, we went through, and on the first slide, as I read the question, I wrote down a table of the answers, right? Or not the answers, but I wrote down a table of the variables. Okay, and here I already converted the brass mass. And so I'll show you how to do that. But I have my brass right here. I have the mass, I have the specific heat, I have the initial temperature, and I want to find the final temperature. For the water, I have the mass, I have the specific heat, I have the temperature initial, and I want to find that final temperature. Now remember, the final temperature, this number is going to be exactly the same because of that heat's going to be transferred until they're both the same temperature, that thermal equilibrium. Okay, so I will show you really quick how I got this M mass number. Okay, so I took the brass piece right here, which is 15.2 centimeters cubed, and this is the brass, and then I used the density. So this density here is 8.40 grams of brass divided by 1 centimeter cubed of brass. Okay, and notice I have my units and labels on every single number. That's going to help you keep things straight of what's going on. So here the brass cancels with the brass, the centimeter cubed cancels with the centimeter cubed, and I rearrange the density this way because I need to have those centimeters cubed on the bottom to convert this from centimeters cubed to grams. Okay, next I took 15.2 and I multiplied by 8.40 grams, and so my answer is 127.68 grams of brass. Okay, now see how I put that number small, the 0.68. Okay, that's because my calculator gives me that that whole number, right? But when I look at significant figures, this has 1, 2, 3 significant figures. This has 1, 2, 3 significant figures. So my answer should only have 3 significant figures. But if I round early, it's going to mess up my calculation. So what I want to do is wait and round at the end. So for me to keep track of my significant figures, that this has 1, 2, 3 significant figures, I write this number small because they're insignificant, but I'm going to use them in my calculation. Okay, so that's why you'll see me writing this small. Okay, so here I've got these two things, and remember from the last slide, negative Q of the brass is going to equal positive Q of the water, and Q equals MCS delta T. So here I'm going to go negative MCS, and delta T is T final minus T initial, and this is for the brass, and that's going to equal positive MCS T final minus T initial. Okay, so now when you guys put these in, always write your units and labels on every single number, and we'll kind of talk through how that works. So what I'm going to do is take all the information for the brass and put it on one side, and all the information for the water and put it on the other side. You cannot mix these things up, okay? So make sure that you keep them separate. So here I'm going to have negative, and the mass of the brass is 127.68 grams. And I'm going to leave off the labels, but I know that everything on this side is for the brass. So I have 127.68 grams for the brass. My specific heat is 0.385 joules per gram degrees Celsius times TF, which is 163, which is what I'm trying to find. So TF minus 163 degrees Celsius. Okay, so that's all on one side of the equation. And that's going to equal, and I'm just going to write it down here, positive, the mass of the water is 150.0 grams. The specific heat is 4.18 joules per gram degrees Celsius, multiplied by TF minus 22.4 degrees Celsius. Okay, so all of this right here has to do with the brass, and all of this right here has to do with the water. Okay, so you got to keep those separate. And we're solving for TF, which is going to be exactly the same in both cases because of that thermal equilibrium. Okay, so I'm going to go to the next slide where it's a little bit written out clear. So here I have negative Q of the brass equals positive Q of the water. And then everything on this side is the brass. So I have M for the brass, I have CS for the brass, and I have delta T. This is all for the brass on this side. And then over here I have M for the water, I have CS for the water, I have delta T for the water. So all of this is the water. Now we have to go through and do all of the calculations, right? So this is where the algebra part is going to get a little crazy, okay? So the first thing I'm going to do is multiply this number by that number. When I multiply those numbers together, grams on the top here is going to cancel with grams on the bottom. So this number right here, I get negative 49.1, there's 3 significant figures, 6 lowercase, or small, grams over degrees Celsius. Or joules, sorry, over degrees Celsius. My grams cancel, okay? Now I multiply that by TF minus 163 degrees Celsius. And I'm going to put that just like that. Okay. Next, I'm going to take and multiply this number by that number. Again, my grams are at the top here and at the bottom here, so they cancel. So this number is 627 joules per degree Celsius. And I write TF minus 22.4 degrees Celsius. Okay, so now my next step, what I'm going to do is move this negative sign, that's a -1, and I'm going to move it on the inside, okay? So that makes this negative 49.16. So when I do that, what I'm going to do is multiply negative 49.16 by TF, and I'm going to multiply 49.16 by that number. Okay, so when I do that, I get negative 49.16 joules per degree Celsius. I'll make this thick, TF, that's what I'm solving for. Negative 49.16 times a negative 163 gives me a positive number, and that's positive 8,000 There's three significant figures. So 8,012.56 joules. And the reason why it's joules is because this degree Celsius right here is on the bottom, cancels with that degree Celsius right there. Okay, so I did this side for the brass. Now I do the same thing for the water. So I take the 627, I multiply it by TF, and I multiply it by negative 22.4. So I get 627 joules per degree Celsius TF. This is plus, this is minus, so this can be a negative number. And I multiply it out and I get negative 14,000, three significant figures, so 0, 4, 4.8, and joules. Again, I have joules over degree Celsius times the degree Celsius number, so the degree Celsius cancels. Okay, so now I have four things, one for the brass on one side, one for the water on the other side. And now I'm going to combine like variables. Okay, so I like to deal with positive numbers rather than negative numbers. So what I'm going to do is add this number to the water side. And I'm going to add this number right here over to the brass side. Okay, so I'm going to add 49.16 joules per degree Celsius TF. So I'm moving it from this side over here. Whoops, 0.6 joules times degree Celsius TF. And then over here, so when I add those two numbers together, let's do it down here, I get 676.1 joules per degree Celsius TF. Okay, so I just took these two numbers, added them together. Significant figure wise, this one has digits to the ones place, this one has to the tenths place. So my answer should have significant figures to the ones place. So this one, we'll just write it small. Okay, so now I have to move this value here over to the other side. So I do that by adding 14,488 joules. So I bring that over just underneath here. And I want to make sure my decimals line up. So that's an 8, 4, 4, 0, 1, 4. Okay, so when I add this up, this is where my significant figures are. And this is joules. And when you guys add numbers, you can only add numbers that have the same units. Okay, so this number becomes 22,057.36 joules. Okay, so on this side I have my TF value, and on this side I have my joule value. Okay, so very last step, right? I've combined my like terms. The last thing I do is I want to get this TF by itself. Okay, so to do that, I'm going to divide this side by this number. So 676.1, remember that one's little, joules per degree Celsius. When I do that, this cancels to 1. And over here, I'm going to do it to this side. So 676.1 joules per degree Celsius. So when I do this, joules cancels with joules. And I divide those two numbers out, and I get 32.6 degrees Celsius, that's my unit, equals TF. Okay, so this has three significant figures, this has three significant figures, so my answer should be in three significant figures, and it's 32.6 degrees Celsius, and I'm going to go, and so when we looked at this before, remember, our water started at 22.4 degrees Celsius, and our brass started at 163 degrees Celsius. But because the brass has a lower specific heat, it's going to give more heat up easier than water will. And so remember, we decided that the specific heat of water, the final temperature of this mixture was going to be closer to water. And look, it is. So 32.6. So that is how you go through and do that problem with all of the algebra and everything. Let me know if you have any questions.